Hello, this is part 2 of the same lecture, review of Galois theory. I was reviewing the first part to make sure that the sound was okay and you could see the board. I noticed that at the very beginning of that lecture, the thing I was saying is not quite what I wanted to say. The map, so I had this field. What I was trying to say is that there is a map from Kx to this field which sends G to G mod F. So this field essentially consists of residues modulo an irreducible polynomial, and then whatever you're denoting the image of X, that's the root of alpha. So just a small correction. I'm sure you know that theory, so you didn't get confused, but just in case. Now, what I want to do is to do Galois theory of finite fields. Which is very simple, but it is crucial in some sense in number theory, because many questions about prime splitting and so on essentially reduce to a question about how a specific generator acts on whatever you're considering, okay? The so-called Frobenius. All right, so let's take small k, so there is a finite field, and then because k is finite, it has to have positive characteristic, okay, and then since it's a field, the characteristic has to be prime. It is very easy to show. If you haven't seen it, I'll leave it as an exercise. So p characteristic of k, so this has to be prime, p is prime, and then this fact that p is the characteristic means that these elements, so you take one of k and you add it to itself, so that's what I mean by this. These elements are distinct. Okay. So this means that K contains this Fp, and this implies that Fp is in K. This implies that K is a vector space over Fp. Okay. Well, how is it a vector space? You have multiplication in K, so multiplication in K, when you apply to an element of K and an element of Fp, consider it as an element of K, you get the action of Fp on K, and you see that addition satisfies the properties of a vector space if you are acting by this Fp. So it's fairly straightforward. All right, so then if it's a vector space, then it implies that K is isomorphic as vector space to tuples, yeah? Where n is the dimension. So this alpha I are in Fp, okay, n is the dimension of K over Fp, which is by definition, so the degree of K over Fp is defined to be the dimension of K over Fp. So this implies that simply by counting that order of K is Pn. So this I did already in one of the previous lectures. I'm just reminding you to set up what's coming in terms of automorphisms. Alright, so then conversely, if you want to prove that for any given n there is a finite field of order Fp, then you consider so now you take n, and this is 1, and consider the splitting field of x Pn minus x. This polynomial the splitting field is unique up to isomorphism. Okay, so and it exists. So this is part of field theory. So you take this polynomial. It's not necessarily irreducible. In fact, it usually is not irreducible. And then you keep adjoining the roots to Fp, and eventually you get a field that contains all the roots. That's the splitting field. So let's consider the splitting field. Now, the number of roots of this polynomial is Pn, but there are no multiple roots. So if you compute the derivative, you get -1. So this implies all roots are distinct. So let's call the splitting field K, and then the conclusion is that this K has to have at least order Pn. Okay, so now right, so it has order at least Pn, but on the other hand you make an observation. So roots, note that roots of fx form a field, form a subfield and why is that? If you take any two roots, alpha, beta, raise them to Pn minus alpha plus beta. The fact that you're in characteristic P means that Pn commutes with the parentheses, so you can bring this into the parentheses, you get alpha Pn, beta Pn. And then if these are roots, alpha Pn minus alpha is 0, beta Pn minus beta is 0, so you get 0. So alpha plus beta is a root of f. So a sum of two roots is a root, and then you can easily see that a product of two roots is a root, because the product is equal to alpha beta, right? Right. So this small detail I'm leaving to you. This means that, well, the roots form a subfield, and that subfield already contains all the roots. So the conclusion is that the splitting field has exact order Pn. This implies that order of K is Pn. Alright, and then since the splitting field is unique, you conclude that this field, right, the order Pn field is unique, essentially. So 0. Finite field of order Pn exists, and unique up to isomorphism. Maybe in the previous part, when I said that if you start with a finite field of order Pn, then if you start with a finite field, then it has order Pn. One small observation that you can make is that because order of the multiplicative group of K is Pn minus 1, every by Lagrange's theorem, Lagrange implies that alpha Pn minus 1 is equal to 1 for all non-zero alpha in this field, and then you get that elements so K are the roots of xpn, so this is xpn minus x. So really, this field is already the splitting field of this polynomial. So not only it has order Pn, but it is unique up to isomorphism. And then by reversing this argument, what I'm doing here, you look at the splitting field of this polynomial, you conclude that there is a field of that order. So the conclusion is that the finite field of given prime order exists, and it is unique up to isomorphism. So this is an important first theorem in the theory of finite fields. And then you don't have to start with a prime field. If you start with Q, which is Pn, can use the same argument with FQ, and then you just have to consider xqn minus x, and then you get this extension. You get a finite field of this order, and they kind of sit in a lattice that you can draw. Like you have another FQM, and then the smallest field that contains both is some D. Then I will leave it to you to figure out what is this D. Okay, sometimes it is n times n, n times m, but sometimes it's smaller. So as an exercise, you should try to figure out what is this D. The other thing that you should figure out is maybe what's the smallest field that is contained in both. So what's the intersection? So maybe I'll draw this way. So FQN, FQM, so this is FQS. You should figure out what is this S, and this of course includes FQ, so this S is at least 1, well, so there is such a thing, but it can be larger. Alright, so then you can draw a lattice of these fields. Which brings the next two statements that I want to make. For any n, right, from this construction, how did we obtain this field? We obtained this field as the splitting field of, so FQN is the splitting field of XQN minus X. So this is FQX. This is not the same n, of course. Maybe I will change this to began with some power of p. Now, what is the conclusion? That this is the splitting field. Well, the conclusion is 1 Fqn over Fq is Galois. So any extension of a finite field is automatically Galois. Okay? And then for any n, there is a unique extension of Fq of degree n. So unique up to isomorphism. Now, these facts are definitely false for other fields, right? So, if you we already saw that the cube root of 2 is not Galois, and then for this part you can show that these two fields are not isomorphic. And in fact, there are infinitely many non-isomorphic quadratic extensions of Q. So again, this fails. Alright, so finite fields are kind of strange. They're much simpler than other fields. So you would expect that Galois theory also should be very simple for finite fields, and this is true. So what's the statement? The main statement of Galois theory for finite fields is the following. I think I run out of ink. We will just replace this quickly. And continue. There is this theorem. The Galois group of Fqn or Fq is the cyclic group of order n. Alright, so proof. Alright. So, as I mentioned here, this extension is already Galois, so we know that it is Galois. But what do we know about the Galois group? Well, we know that the Galois group has the order of the degree of the extension, right? It's the number of embeddings. So this is n. That's part of Galois theory. We will show that this is cyclic by exhibiting a generator of this group. But, what's the generator? You take this element, tau, that maps Fqn to Fqn, and what's the map? Well, alpha goes to alpha q. Okay, q is this element. So we're considering this as an extension of Fq, and I'm sending alpha to alpha q. Again, by the same reasoning that I applied to the splitting field of this polynomial, well, what's the reasoning? It's not a reasoning, it's a formula really. So this is alpha q plus beta q. So in positive characteristic, if you're raising to p's power, you get this identity. So this means And the same is true for the product. So this is really an automorphism of the field. So this tau, this is an injection, right? If you start with a non-zero alpha, this will be non-zero. Maybe it's not completely clear why this is surjective. And in fact, this will not be surjective. Just a side remark: if you're working with this field, so you take FQT. Okay, so rational functions in determinant T. Then you have the same map, the raising to Q power map. It's again a homomorphism from this field to itself, but it's not an automorphism because it's not surjective. So the image of that map is FQ TQ. So you cannot get this T. But here it is surjective because this is finite and it is injective. And an injective map of a finite set to itself has to be surjective. So you get this. This field is infinite, so there is no contradiction to that statement. All right, so we have one automorphism. Is an automorphism. Now, besides being an automorphism, if you apply this to an element, if alpha is in FQ, well, what are the elements of FQ? These are the elements that are roots of xq minus x, right? So then alpha q is just alpha, by the way this field was constructed. So this automorphism is not just an automorphism of this field, but it fixes FQ pointwise. So it's an element of the Galois group. Hence, tau belongs to the Galois group. Okay. This special element is called the Frobenius. It's called Frobenius automorphism. And what we want to do is to show that this element generates the whole group. Well, to do that, let's just consider the subgroup that is generated by tau. So tau squared, tau cube, tau n. Well, tau n will be 1. And I want to claim that this n is the smallest n for which tau n is 1. If I can prove it, then the cyclic group generated by tau already has order, has the same order as the Galois group, so it has to be the whole group, which implies this theorem. So how do we prove that no smaller power of tau is 1? So assume, by contradiction, tau m is 1, right? And this m is less than n. Then tau m alpha, which is alpha qm, has to be alpha, right? If tau m is 1, then this is alpha. On the other hand, it is alpha to qm for all alpha in fqn. But then this means that all elements of this field satisfy this polynomial. All elements of fqn, or rather any element is a root of xqm minus x. But since this qm is less, qm is strictly less than Qn, yeah, so what you get is that a polynomial of degree Qm has Qn distinct roots, and since all these elements are, and this is a contradiction because over a field a polynomial has at most as many roots as its degree. This cannot happen, and this is the conclusion. So the Galois series is that, right? So you also recover the main theorem of Galois theory from kind of combining a little bit of group theory to whatever we said about finite fields. So there is a unique extension of degree n for each FQ, right? But if you consider this extension in a larger field, you have a cyclic group, and in a cyclic group you have a unique subgroup of order dividing the order of the group. So as an exercise, you should try to reduce the main theorem of Galois theory for FQ from previous considerations, previous discussion. Okay. Now, now let's do an example. Okay, let's apply this Galois theory to a problem that we considered on Tuesday before the spring break. So, example. Let's take L to be a prime. And the question is, how does xp minus 1 plus xp minus 2 x plus 1 split modulo L? And why is this an interesting question? Number theory is because from this theorem of Dedekind that I mentioned, if you consider this extension and you want to understand how this prime L splits, well, what I said is that the main theorem says that you take the polynomial that generate this extension, and we know that the number ring here, R, is in fact generated by one element, and then the way this splits is exactly reflected how this polynomial splits modulo L. So let's understand how we can see this splitting from Galois theory. So to applying a little bit of Galois theory to this question. Now the roots of this, okay, so you have this omega squared, omega p minus 1. Roots of this fx. Now suppose modulo L, this decomposes this fx is equal to some gx and then some hx. So this is in flx. And these are irreducible, both irreducible and both belong to this ring. Okay? what can we say about Gx? Well, it has coefficients in FL, which means that if I apply the Frobenius, which is the Galois element, the generator of the Galois group of the splitting field of Gx, then that element fixes the coefficients, because the coefficients are in FL. So Gx irreducible is coefficient in FL. And then you have this FL and you have this K. This is the splitting field of G. The order is here something, and the degree, and that's the degree of this G. But it is generated, the Galois group is generated by the Frobenius. So the Frobenius is the element, the smallest field that is fixed by the Frobenius is this FL, which means if I'm applying the Frobenius to the roots of Gx, what should be happening? Well, first of all, the roots get permuted between themselves, right? But there is just one cycle. So when you're applying this, the Frobenius tau, all the roots get permuted transitively. This is important, because if there are two separate cycles, if you separate them and write a polynomial which has each cycle as its sets of roots, the coefficients of that polynomial will be fixed by the Frobenius, so they will be in FL. So let me do this more explicitly. Okay, so all the roots, all the omegas, they are indistinguishable from each other because each of them is a primitive root. Now I take my tau, okay, and I apply to omega. I get omega L. Now, what is this omega L? Well, this is really equal to omega to L mod P. So if L is larger than P, this is one of the powers of omega from 1 to P minus 1. But let's write it omega L for now. And then you apply tau again. So you get omega L, omega L squared, omega Ls. Eventually, right, you cannot be getting different elements every time, so eventually you will have to get omega back. If you get something else, right, if Ls is equal to omega Lk or S prime, then you simply divide by the power, and you get that you will get something small that is equal to omega. So this is omega. So S is the smallest element for which this happens. I hope this is okay. You should think about sort of why do you get omega and why not like L squared the first time? So why the repetition comes back to omega? All right. So this is part of this set. Okay, but if I form now this polynomial, this Gx, x minus omega L x minus omega ls, ls minus 1. Yeah. Then, well, and what can I say about the coefficients of this polynomial? The coefficients are obtained as symmetric functions in these roots. And if you're applying tau, you're just permuting these omegas, right? They get moved around, but the polynomial does not change, which means that its coefficients do not change. So this means that this polynomial has coefficients in Fl. Okay, so this way I can see one of the reducible factors of fx. So I have this fx, I had some primitive root, and by using the Frobenius conjugates of this root, I produced an irreducible factor of fx. And then there is this hx. Now hx has some other primitive root, some other primitive piece root as one of its roots. And then I can apply exactly the same argument. In some sense, I did not use the fact that there is a specific omega. I did not specify which omega I chose. It doesn't matter. Okay, so then these hx will split. There will be a polynomial similar to gx, and it will have exactly the same order, because this cycle, the number of times you have to apply Frobenius to omega to get a full cycle, does not depend on the choice of omega. Well, what does it depend on? It depends on when this will be congruent to 1 modulo p. So S is the smallest integer such that omega ls is omega, which is equivalent to omega ls minus 1 being 1, which is equivalent to smallest s such that p divides ls minus 1. And this is the same as order of L modulo P. Now, what I was saying, that it does not depend which omega you choose. How do you see this? I did not use anything specific about omega, except that it's a primitive piece root of 1, right? So its piece power is 1, but not any small power. And all of them have that property. So if I just apply the same argument with omega I will see the same, I will reach the same conclusion. So omega ls equal omega well, yeah, so omega ls minus 1 equal 1 if and only if omega I ls minus 1 equal 1. that's my claim. So this S will be the same. Doesn't matter which power of omega you choose. And how do you see this? Well, P divides Ls minus 1 if and only if P divides I Ls minus 1 if this I is between P minus 1 and 1. Right? So it doesn't matter if I put an extra I here because I is smaller than P minus 1, it is coprime to P. So these two statements are equivalent. Right, so the conclusion from these considerations, what you conclude is that this is theorem xp minus 1 plus xp splits into p minus 1 s irreducible polynomials splits into p minus 1 s polynomials of degree s, where s is the order of L mod P. Right, so here's a quick example. Let's take P to be 5, then L equals 3. So how do you compute the order? You keep raising this to powers. So this is 4, and then 3 cubed is congruent to 2, and then 3 fourth is congruent to 1. So this has order 4, right? So the group L equals 3 has order 4 modulo 5. So it generates 3 generates F5. The multiplicative group of 5 elements is actually a cyclic group, which means that the cyclotomic polynomial is irreducible. There is a conclusion that you can check directly, is irreducible. Over F3, over F5, yeah, over F3. Maybe I should write generates Z mod 5Z, the multiplicative group of this ring. Similarly, L11 has order 1, mod 5, and 19 has order 2, mod 5. So you can check these things. Now, what's the conclusion about the splitting? The conclusion is that if I consider this extension Q omega, and this is omega by 1, so this is a degree 4 extension, then 3 remains prime. If I consider 11, it splits into 4 primes. So it splits completely, P1, P2, P3, P4, yeah. And if I consider 19, then this splits into 2 primes. 3 is prime. In R 11 is P1, P2, P3, P4. And the residue degree, or the inertial degree, is 1. So, and this 19 is equal to Q1, Q2. And the inertial degree is 2, meaning that R mod Pi, this is really the same as Z mod 11, but R mod Qi is isomorphic to F19 squared. This is F11. And R mod P is isomorphic to F3, 4. Okay, so it has this order because it remains prime. So hopefully this is a better explanation. You can ask me for the details. If you didn't understand something, I'll be happy to explain again how this works. So this was the main thing I wanted to do. Now we'll take a short break, and then there is a small part that remains. I will do that, and that will be it.